Alright y'all, hello and welcome to homework video number 16. We are working with verifying our trig equations here. If I were you, I would make sure that I had right next to me my triangle functions toolkit, which should say trig functions toolkit, but like most things, this has a typo in it. So make sure you have this next to you because it has all the trig identities that you will need to make sure that you can simplify these. Okay? So this first one says prove the equation below, and speaking of typos, I wrote this as tan x. It should be tangent of x. So looking at this one, I see that there's a fraction built into this. I don't see anything that I can factor, so I'm going to skip over this, but I do see a fraction. Okay, so I'm going to see how I can rewrite my identities here with my reciprocal identities. First thing I see is secant of x, sec of x. I'm going to go over here and see that secant of x is the same as 1 over cosine. Okay? So I'm going to take secant of x, and I'm going to rewrite that as 1 over cosine of x. Okay? And then I see cosecant here. Cosecant, I'm going to put this one in blue. I see that that is the same thing. Cosecant, CSC, is the same as 1 over sine. So I'm going to write that as all of that as 1 over sine of x. And I have that equal to tangent of x. So equal to tangent of x. Well, right now, I haven't made anything else in common. Cosine and sine don't have anything in common. So I want to see if I can rewrite tangent so that it has something in common with cosine and sine. So I'm going to look here and I see two different identities for tangent. I could write it as 1 over cotangent, or I could write it as sine over sine, or sine over cosine. I'm going to pick sine over cosine because that would make this side of my equation have something in common with this side of my equation. So I'm going to choose to write tangent as sine of x over cosine of x. Okay? Now here we've got our identities. From here we're just going to simplify. Remember, when I am dividing a fraction by a fraction, I do my same, change, flip. My first fraction stays the same, so my first fraction stays the same, 1 over cosine of x. I change division to multiplication, and my second fraction, or my denominator fraction, flips. So this becomes sine of x over 1. And I still need that to be equal to sine of x over cosine x. Now that I've done my same change flip, I'm multiplying fractions, so I know I can multiply straight across, okay? Which will give me, I'm running out of room here, but I would get sine of x over cosine x is equal to sine of x over cosine x, okay? So I have proved it here. You can leave your answer like that, or to refer back to your original, I was trying to get it equal to tangent. Well, I know based on my identities, sine over cosine is the same thing as tangent. So if I wanted to, I could rewrite this as tangent of x is equal to tangent of x. Either one of these is correct. Okay, that's just another way to prove that your original one was correct. Okay. So that is just a simplifying using our reciprocal identities review. Next one we are going to do together is this middle one here that says verify. This gets a few more identities into it. I have already written out the work here. I'm just going to write out the reasoning. Okay, you are expected to write down your reasons for every step here as well, because there are multiple ways to solve these, so there are multiple different lines of reasoning that you can use. So if I look at this, it says verify, cosine x plus sine x times tangent x equals secant x. So I'm looking at this. The first step is I'm going to pick this side of the equation to simplify. So I pick the left side to simplify. Okay, pick the left side to simplify because it's going to be easier to simplify this and make it look like the right side than the other way around. So the first thing I am going to do is I'm going to take tangent of x, and I'm going to rewrite it as sine of x over cosine x, because I know that that is one of my identities. Tangent is the same thing as sine over cosine. So the reason that I do that, I rewrite tangent of x as sine of x over cosine x, so that my equation has sine in common now. Okay, so now I have sine in common with the two that I'm multiplying. Okay, I can write sine of x over 1, and this is multiplication happening here from the beginning. When I multiply fractions, I multiply straight across. Sine of x times sine of x is going to give me sine squared of x. So I multiplied my fractions. Okay. From here, what I'm going to do, I'm going to write cosine x over 1. The tricky thing here is these are being added. When I add fractions, I have to have a common denominator. So what I do here is I multiply both sides, or I multiply this fraction by cosine x over cosine x, because I need the denominators to match. So my reasoning here is common denominator to add fractions. So what I look at is this fraction has cosine x in it. This fraction does not. So I need to multiply the bottom of this by cosine x. If I multiply the bottom by cosine x, I have to multiply the top by cosine x. That's exactly what's happening here. Okay? From there, I multiply fractions. So I multiplied this fraction times this fraction. Cosine x times cosine x gives me cosine x squared. 1 times cosine x leaves me cosine x in the bottom. Okay? Well, now after I multiplied my fractions, I now have a common denominator. Okay, cosine x is my denominator for both fractions, which means that I can actually add these fractions now, which is what I do here. Add fractions. So I add the tops of the fraction and keep the bottom of the fraction the same. Then I look at, okay, I want to see if I can simplify this, because my whole goal is to get this to look like secant of x, right? We're just working with the left-hand side of the equation now. Well, I want to look and see if there's anything about this that I can simplify, okay? So I see cosine squared x plus sine squared of x, and if I see that, that looks like a similar identity to me. That looks like my Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. So I know that I can use my Pythagorean identity here and replace this with 1, which is 1 cosine x. Now I'm going to bring back the other side of my equation. This right-hand side that I was trying to get it to match is equal to secant of x. This one's really, really, really close to being the same. So I'm going to look, I see this as a fraction, so I'm going to go look at my reciprocal identities again, and I see 1 over cosine x is the same as secant. So here I use my reciprocal identity. That is 1 over cosine x is equal to secant x. So I replace it here, equals secant x. My equation is verified. Okay? So again, it's a lot of logic. It's a lot of changing things out until you get something in common so that you can simplify. Last one we'll do on the front side is an ACT problem about combining like terms. These look a little bit tricky. You see a subtraction sign happening here. I always write in a -1. I've got a -1 on the outside of parentheses, which means I should distribute into parentheses. My first fraction remains exactly the same. Excuse me, my first term remains exactly the same. I've got a. If there's nothing there, I can write that in as a coefficient of 1. So 1a plus 2b plus 3c Now that I've distributed the negative, this becomes an addition problem. Negative 1 times 4a is negative 4a. Negative 1 times 6b is negative 6b. Negative 1 times negative 5c is positive 5c. And I lined them up where my like terms are in the same column, so I can add straight down. 1a plus negative 4a is negative 3a. 2b plus negative 6b is negative 4b. And 3c plus 5c is 8c. So my correct answer here is E. So this is all about combining your like terms. Just make sure you distribute that one first. Okay? Now to the back of the homework. We're going to be looking at this problem first. Flip over to make sure I have mine correct. Looking at this problem first. Okay? This is one of our addition problems, which means we're going to have to get a common denominator here. So this says prove the equation below, so I know that I'm verifying. I'm going to write these as fractions first because it helps me see that they don't have a common denominator. So I'm going to write this as cosine x over 1 plus I'm going to switch tangent of x using one of my reciprocal identities to sine over cosine. I'm going to write it as sine of x over cosine x because now these have something in common and tangent is written as a fraction now. Okay, is equal to the other side of the equation, cosine squared x plus sine x all over cosine x. Okay, I cannot add these fractions as they are right now because they do not have a common denominator, so I need to make them have a common denominator. When I'm looking at this, I see that cosine x is the denominator here and 1 is the denominator here. So what this denominator is missing is a cosine. So I'm going to multiply the bottom of the fraction by cosine x. If I multiply the bottom of the fraction by cosine x, I have to multiply the top of the fraction by cosine x as well. So when I multiply these together, cosine x times another cosine x is going to give me cosine squared x. All of that over cosine x times 1 is just cosine x. And this fraction stays absolutely the same because it already has the denominator that we need. Now that our denominators are the same, we can combine these. When we combine them, we write it as a single denominator. So my denominator that I got the same, one denominator. And then I add the numerators, cosine squared x plus sine of x. And that now matches exactly the other side of my equation, cosine squared x plus sine x all over cosine x. So I have verified this to be true because the left-hand side looks exactly like the right-hand side. Tricky part about this one is making sure you get that common denominator. Alrighty, very last one here that we'll go over besides the ACT problem at the bottom. This one is a doozy and is probably a little bit harder than one of the ones that I should have put on the homework, but I'm going to go through it with you, so we're going to figure it out together. Okay, so first thing, our first step here, I've got verify this side of the equation is equal to this side of the equation. I can see already that I might use one of my double angle identities here, so we'll start there. Okay, so I'm going to first pick the left-hand side of the equation. So step one is I'm going to simplify the left-hand side because I think I can simplify this to match this easier than the other way around. So I'm going to pick the left-hand side to simplify. First thing that I'm going to do, I see that this is one of my double angle identities. Cosine 2 theta is one of my double angle identities. So if I look here, I see cosine 2 theta, and then it could be this option, or this option. Okay? The one that I am going to choose is cosine squared theta minus sine squared theta because I see sine theta plus cosine. These are the ones that look the most similar to me in terms of having something in common between the numerator and denominator. Because of that, that's the identity that I'm going to choose. So I'm going to rewrite this as cosine squared theta minus sine squared theta, all of that over sine theta plus cosine theta. Okay? So I used a double angle identity here, so that the top and bottom would have something in common. Okay? So from here, this is where the fun stuff happens. I see a squared minus a squared. This is my special case no b value. I know that's really, really hard to see because of the trig identities we're using here, but our highest exponent is 2. Okay, our highest exponent is 2, and we're subtracting out sine squared, which is also a perfect square. So if you think about it this way, we always use special case no b value with equations like this or factors like this. This number is always what's called a perfect square. That means we can take the square root of it. Okay? We could really rewrite this as x squared minus 2 squared because 4 is a perfect square. Another example would be like x squared minus 64. We could rewrite that as x squared minus 8 squared because if we take the square root of 64, we get 8. So this is one of our special case no b values here because both of them are being squared. So we're going to factor the top of this. My a value times my c value gives me negative cosine squared theta sine squared of theta in the top, 0 as my b value in the bottom. My two factors are going to be cosine squared x and negative sine squared, theta, negative sine squared theta, because those multiply to the top and add to 0 in the bottom. Okay? So we can think about it this way, or we can also just think about taking the square root of it. They multiply to this in the top, they create 0 in the bottom. So, from here, we are going to write this in our factored form as sine or cosine of theta plus sine theta, cosine theta minus sine theta. And all of that over our denominator of sine theta plus cosine theta. Okay, and we can see here that these will cancel in the top and bottom of our fraction. So I'm left with cosine theta minus sine theta is equal to cosine theta minus sine theta from the right-hand side of my equation above. Again, this is much more complex than we've gotten into, which is why I'm giving it to you as an example problem here. And you're responsible for trying this problem on the right, which is not quite as complex as this one. This is just something that I wanted to expose you to and have us see that a difference of squares or our special case no b value can look confusing when we add in our trig values. So what I want us to look at next, these shouldn't be squared. This should be cosine theta and negative sine theta. Okay? What I want us to look at next is one more example of an ACT problem of combining like terms. This one's a little different because if it's right next to the parentheses, we know it means multiplication. So we just have to distribute into our parentheses. Negative 8 times negative 7 is negative 56. X to the third times x to the sixth. If we're multiplying like bases, we add our exponents. So 6 plus 3 is 9. Negative 8 times negative 3 is positive 24. 3 plus 5, again, when multiplying like bases, we add our exponents. 3 plus 5 gives me x to the 8th. My correct answer here is, if I can read these exponents right, is B. Okay, that is it for the homework video. If this problem is confusing to you, that is okay. I wanted to expose us to a problem like this. But it is not something you will be responsible for on the homework quiz. Okay, that's it. As per usual, like and subscribe.